thank you for joining us for the fall UC Irvine School of Medicine Dean's Distinguished Lecture Series. For those of you who haven't met yet, I'm Dr. Michael Stamos. I'm the Dean of the School of Medicine here. The Dean's Distinguished Lecture Series was established in 2019 with the idea of bringing together influential leaders, thought leaders from healthcare and academia to share their insights, their experience, their innovations, and anecdotes with our faculty, our staff, our students, and community members alike. The intention is that each year we'll have one speaker representing innovation in basic sciences, one representing advances in clinical medicine, and one speaking on developments in clinical research. I'm honored to welcome tonight's speaker, Dr. Leroy Hood, MD, PhD, a renowned scientist and engaging researcher and speaker. He'll be sharing his insights, his experience, and his vision in his presentation titled, Data-Driven Individual Health Can Profoundly Change Your Life, if you let it. I ask that you hold your questions until the end of the talk, when we will have microphones available so everyone can share in a Q&A. Before we begin, please be aware this is being recorded. The full recording will be available to all of us on our website soon, but also it will capture anything anybody says, so be aware of that. Without further ado, I'd like to invite Dr. Shaista Malik to formally introduce our speaker. Dr. Malik is our founding executive director of the Susan Samueli Integrative Health Institute and our Associate Vice Chancellor of the Susan and Henry Samueli College of Health Sciences here at UC Irvine. So thank you, Dr. Malik, for doing the formal introduction of our speaker.
Thank you, Dean Stamos, and welcome everyone to our Dean's Distinguished Lecture Series community lecture. It's my great pleasure now to introduce someone that I hold in the highest esteem. He's an inspiration to so many scientists in the field of systems biology, precision medicine, integrative health. And he was here, I think I told some of you this story earlier, he was here back in 2014 when then Dean Ralph Klayman invited him to give a talk at the Beckman Institute. And he was talking about P4 medicine, about multiomics, and I was writing my first R01 NIH grant. I don't know if you remember that, Dean Klayman. And so I was an assistant professor back then and writing this grant that I thought there was just no way that anybody would understand what I was talking about. And I went up to Dr. Hood after his lecture, and he's like, "You're onto something." And I submitted that grant, got that grant. But Dr. Hood is just an incredible, world-renowned scientist. He has the 2011 National Medal of Science. He's a developer of several groundbreaking scientific instruments that made possible major advances in biological and medical sciences. He also co-founded the Institute for Systems Biology. He really created the field of systems biology in 2000 and served as its first president until 2017, where he still serves as a distinguished professor. Additionally, he's the CEO of Phenome Health, a nonprofit research organization taking a data-driven approach to better understanding human health and biology, tackling some of the biggest challenges facing medicine and healthcare today. Even more remarkably, Dr. Hood has been elected to the National Academy of Sciences, the National Academy of Engineering, and the National Academy of Medicine. And of the 6,000 scientists that are part of the national academies, only 20 ever have held all three, have been elected to all three academies, and Dr. Hood is one of them. He received his MD from Johns Hopkins School of Medicine and his PhD in biochemistry from Caltech, where he was a faculty member from 1967 to 1992, serving for 10 years as the chair of biology. I also learned while he was at Caltech, he played football for the team there. And he played in 16 Super Bowl games. That's more than most professional football players. Oh, sorry, Rose Bowl. This is how much I know about football. So, Rose Bowl. And he also does 200 push-ups every day. He's just phenomenal in every way possible. He, while at Caltech, helped to develop 4 sequencers and synthesizer instruments that paved the way for the Human Genome Project. He and his students also deciphered many of the complex mechanisms of antibody diversification. He's currently carrying out studies in Alzheimer's disease, cancer, and wellness. He's pioneering a 1 million patient genome Phenome project and is bringing scientific wellness to a contemporary U.S. healthcare system. He's played a role in founding 15 biotech companies, including Amgen, Applied Biosystems, Aravel, and NanoString, and he just shared with us earlier today he's co-founding yet another company that he's probably going to give us a talk about. He's published more than 850 articles and currently holds 36 patents. I could keep going on, but I'm going to have Dr. Hood come and join us and give us his talk. Thank you, Dr. Hood.
Well, what a pleasure to be at an institute that believes in integrative medicine. So I salute all of you here in that endeavor. And ready to go, okay? So what I'd like to do is give you a real sense of what data-driven science is and leave you with the idea that you're responsible for learning enough about your health to optimize it. And that's an enormous responsibility. In the short term, you'll feel better. In the longer term, we hope to have a health span that extends into the 90s where you can be functional right up to the very end. But the whole question of how you persuade people to do what is absolutely best for them is really a fascinating and unsolved problem, largely. So let's see if we get there. Yeah. So I started in 2021 this nonprofit called Phenome Health, and it's the focus now for about 20 people to take these data-driven approaches that I'll talk about in this lecture and so forth. And what I really hope to be able to do is give you a story history of how I've gone about thinking about this and bringing you up to date on where we are today, but most important, having you realize where we're going to be in just a few more years. And the ultimate objective is to create a healthcare that's dedicated to optimizing your wellness and avoiding disease completely. And that's very different from a healthcare today that at the 97% level is focused on disease. So how do we go about doing that? I remember coming to Caltech as a young assistant professor in roughly 1970. And as we heard, young assistant professors always like to look ahead and figure out what the whole future is all about. And I was really very interested in human complexity and convinced it was an enormous barrier to understanding both wellness and disease at that point in time. And I think that's illustrated by this parable of the elephant and the 5 blind men all feeling a different part of the elephant. And each of them describing the elephant in the context of what they felt. And of course, that was very much like medicine was at that time. You could make a lot of observations on the outside. At that time, you couldn't make very many observations on the inside, and that's really a key part of health in every way. But what I decided is human complexity could only be solved by developing technologies that let you make lots of measurements on human beings. And I was utterly convinced at that time that the real key to human biology in many ways was the blood, because it's a system that bathes all organs, Organs secrete molecules into the blood, and in that sense, you have access to them, especially if you can identify those molecules and the sources from which they come. And now we can do that in very interesting ways. And the final point, of course, was this whole idea. If you take the blood and you generate lots and lots and lots of measurements, what do you do with it? And the thinking at that time was kind of inchoate, but it evolved later to be systems biology. And the idea of systems biology is really dirt simple. It's the idea, if you wanted to understand how a car worked, what would you do? One, you'd define all the parts of the car. Number two, you'd ask how the parts are interconnected. And three, you'd ask what the parts do when the car does its function. And those are the essence of systems biology, and in exactly the same way, we can ask about wellness and disease in that context. Only a human being is infinitely more complex than a car is. The other thing I realized in reading in 1973 this very famous book on paradigm changes by Thomas Kuhn, that we were going to have to go through a whole series of paradigm changes if we'd ever get to deciphering complexity. And in my career, I've gone through 8 paradigm changes that I'll define. 7 of them I'll talk about tonight. And each of those paradigm changes was met with enormous skepticism. And I think one of the most important things that a scientist has to have, apart from a big idea you'd like to focus on, is determined optimism to carry forward in the face of people who are telling you it's ridiculous. And you'll see with some of these things. So we developed over a period of about 30 years, starting my time in 1970 at Caltech, 6 instruments for basically reading and writing DNA and proteins. And these instruments really laid the framework for all of contemporary modern molecular biology, but one of them was really key in beginning to decipher the complexity of human beings, and that's the automated DNA sequencer, which really made the Genome Project possible. And that's why I got invited to the first meeting ever held on the Human Genome Project in the spring of 1985, where Robert Sinsheimer assembled 12 scientists to pass judgment on the Human Genome Project. And we came to 2 interesting conclusions. One is it was very difficult to imagine how it would be done at the time, but technically feasible. And 2, we were split 6-6 on whether it was a good idea or not. And the objections were that the 6 opposing it were terrified that big science would swallow up small science. And the Genome Project was the first big science project. I'll say parenthetically, so I got involved in starting it, and one of the key strategies for persuading people to do this project, and let me say the National Institutes of Health opposed it up until the very end when it was decided to be done, for really interesting reasons that we can talk about. But DOE really pioneered the early things. And the absolute key decision in the Human Genome Project was when 6 of us went in and persuaded Senator Domenici of New Mexico that this Human Genome Project should have $3 billion of new money, so the opponents couldn't say we were taking money away from other aspects of biology. And that actually changed the tenor and attitude of a lot of people at that time. And of course, the human genome is absolutely key to individual health in many ways that we'll talk about in just a few moments. The next thing that happened was, again, to show you how good institutions can really be stubbornly recalcitrant, is the senior biologist at Caltech utterly opposed me being in biology because I had a relatively large lab, because I needed cross-disciplinarity to do all these instruments that we did. And they came to the chairman and said, we think you should move him to engineering. And of course, I said, no, I'm a biologist. I refuse to go. And so I went back to them and said, okay, if that's your attitude, let me start an applied biology department at Caltech where the different faculty members will be all these cross-disciplinary people and we can drive the technology there. And all of the other divisions at Caltech loved the idea, and biology vetoed it. And it was clear they didn't want any kind of competition. But there's hope. 20 years later, they've done almost precisely what I suggested we do back in 1988 or whenever it was. But what happened is Bill Gates made it possible to move to the University of Washington and set up this cross-disciplinary department. It was called Molecular Biotechnology, and it was absolutely spectacular. Phil Green wrote the key software for the Human Genome Project, how you determine the quality of DNA that's been sequenced and how you assemble the fragments. Rudy Abersole and John Yates pioneered the newly emerging field of proteomics and did the first two major techniques in that area. And we actually invented the inkjet technology for DNA synthesis that Agilent uses today, that's very high-scale DNA synthesis. And I'm going to talk about why that's a really important instrument tomorrow. I won't get into that. But this department was enormously successful, but what I really wanted to do with the department is embed in it systems biology, because I thought more and more about what that was about. And I found at the University of Washington, it was big and bureaucratic and clunky, and the IP people didn't know a whit about starting companies or doing things like that. So I decided, look, if I was ever going to get anything done, I'd have to set up an institute to do systems biology, and I resigned in 2000 and did that, and set up the Systems Biology Institute with all the characteristics. And we published the first classic paper in yeast biology with galactose on how to use systems biology to understand very deeply the dynamics of galactose utilization. And in a second paper, we studied scrapie in mice, which was an inducible neurodegenerative disease. And we were able to beautifully map the coordinately integrated disease-perturbed networks beautifully with the pathophysiology of the disease. And that, I think, convinced most people it was absolutely going to be seminal. And in the early 2000s, I started thinking not just about systems biology, but about healthcare as well, and proposed this idea of P4 healthcare: predictive, preventive, personalized, and participatory. And the first three Ps are all biology, and we really know how to do them now, and I'll try and convince you of that. The fourth P, how you persuade people to change, is the big puzzle. And we'll talk about some of the ideas we have about that as well. What happened that was really very interesting is P4 opened up a whole series of possible new strategies and technologies for deciphering human complexity. And I put a whole series of grants into NIH, and almost every one of them came back and said, you haven't proven you can do this. This is too far ahead of its time. We're not interested in these kind of things. So I decided the only way to get around that roadblock was to go to countries and try and argue that if we set up an institute for systems biology in the country, they could in turn give us money to do P4 strategies and technologies. So I went to 4 countries initially, and each of them is a great story and failed in all 4 countries for 4 really different reasons. But the 5th country was Luxembourg. And this was a jackpot because a friend at PricewaterhouseCoopers said, you ought to call up my friend who's the Minister of Economy who really wants to transform and bring to Luxembourg modern biology. So we had a 45-minute conversation. He said, I love what you're talking about. Why don't you write a proposal to me? So I said, what are the limits of the proposal? And he said, there are no limits, just ask for what you need. So I asked for 100 million, and we got 100 million over a 5-year period. And we were able actually to do all the things we needed to do, just thinking about individual population, data generation, and everything. And it was in 2013 when I persuaded 108 of my friends to go through this genome and phenome analysis for a year to see if it worked. And I went to Francis Collins at NIH and I said, look, I'd like to do this wellness study on these people. What do you think? And he said, Lee, the role of NIH is to study disease. It's not to study wellness. And I said, I think it's been misnamed then, hasn't it? The National Institutes of Health, which really annoyed him. But anyway, we went back and used philanthropy to prove the principle. And then we actually started a company called Airvale from 15 to 19 that generated 5,000 patients with all of these data. And that's a lot of what we'll talk about in the future. So the paradigm change there was data-driven analysis. And then I decided what I'd really like to do is see if I could go to a big hospital system and bring what we call scientific wellness or quantitative wellness and genomics. And the CEO of Providence, 51 hospital system in 7 Western states, seemed to be ideal, headquartered in Seattle and all. And I spent about 4 years there. And I'll sum it all up by saying, I never knew different people could have so many ways to resist change in all dimensions. And so in 21, I said, okay, I'm out of here, and started Phenome Health. And that's what we have driven things with since. And the big new change after leaving a healthcare system and setting up this new approach to it was the realization we'd never be able to really push the idea of data-driven health to its endpoint, which is scientific wellness. That includes optimizing wellness and avoiding disease, unless we had a continuation of the Human Genome Project, which we'll call the Human Phenome Project. And we'll talk about that and why that is so important in the future. But that's kind of the history and what things are all about. Now, the lesson I learned in 6 out of 7 of these paradigm changes is small, agile institutions are really what changes science in big ways. The exception was the Human Genome Project, because that came from many different kind of people, but all the rest of these things were. And the small institutions can either be nonprofits, and I've started a series of different nonprofits, or they can be for-profits, and these various ones have been useful. And the idea that I fundamentally believe in, the 2 key ideas that I think are really important, are one, since society pays our salaries, our obligation is to give back to society things that will be useful for them. And we can do it in a lot of different ways, but starting companies is one focused way. And I think the other thing that's really key is anytime the government pays for data, the data should be available to everyone. And that's absolutely going to be critical on human-based data in the future. And one of the things that we really struggle against are companies that are generating a lot of human-based data that have real constraints on it, as opposed to the governments that are making it more open and free. And that's a point of contentiousness and everything. So what about this idea of health? I think it's really important to realize that health optimizes every single human activity in really marvelous ways. I mean, from development to education to jobs to community to creativity. The whole business is always optimized by really being healthy. So I think healthy individuals is really key. And I think this data-driven health that uses the genome and the phenome of each individual to analyze that data, and from those data to derive the unique set of actionable possibilities that will let the individual optimize their wellness and or avoid disease. And I'll tell you, all of us have tens to hundreds of these kind of optional things, and you can prioritize them with regard to things that are in relative importance. And I will say that health really has three dimensions, and we'll really emphasize this a little bit later on. So one dimension of health is your wellness and optimizing it. Another dimension is the disease that you have. And a really important dimension is that transition. And the key point about the transition is to detect it as early as possible so we can reverse it before it ever becomes clinically manifest. And we'll show you exactly. We can do this in three ways, and I'm only going to talk about one of them, but the most obvious one I'll talk about. And the ultimate goal is to generate a health span of 90 to 100 or so. And a really interesting statistic is in the last 40 years, American lifespan has increased by 10 years from the low 70s to the low 80s now. Its health span has increased by 0 years. So you have more and more people going out to be either caretakers or taken care of. And that certainly has to change in the future, and that's going to be very important. So the genome for the individual, in a sense, gives you a framework for what your health trajectory can be, okay? And the phenome of the individual is what happens from birth to death and how you change. And the two things that really regulate the phenome and its changes are, one, your personal behavior, and two, your environment. And those are absolutely key measurements, and we have lots of ways we can measure those things, from blood analytes and the gut microbiome and various kinds of digital health assays and so forth. But the really important point is there are a couple of really major genetics papers that have come out that have asked the question, what is the relative contribution of the genome as opposed to the phenome to an individual's health? And the answer is, I'll come to that in just a sec. The genome is roughly a 10% contributor, and the phenome is a 90% contributor. So all the common diseases are initiated in the phenome with some reasonable kinds of exceptions. And the final point I would make here is this million-person project I've talked about, looking for 10 years at genome and phenome, is really key, because that'll give us the data we need to really compellingly prove that data-driven health is going to be the future. And I'll talk a little bit later about the details of that and everything. So let me just say a word about systems biology and the importance of blood as an assay of looking at all the different kinds of organs. One thing we've done is we've identified organ-specific blood proteins for more than 25 different organs. So what that gives us the ability to do is for each of those organs to look at state changes from wellness to disease. And that's turned out to be a very, very powerful kind of tool. But it makes the blood a real window into wellness and disease and so forth. And with the Airvale people and the 5,000 individuals we looked at over 4 years, you gain an enormous amount of data. And you, of course, can approach it in two major kind of ways now. One is to use the systems biology, which translates the data into the dynamic networks that underpin normal and disease physiology. And a second way that I'll talk about tomorrow, I won't go into detail now, is you can use the statistical associations in these data to aggregate together the different types of data in ways I'll show you in just a few minutes about. And I'll give you an example of, I was in the Airvale program, and one of the striking associations that I noticed in my own physiology were 2 gene variants, each of which were very effective in blocking the uptake of vitamin D with a level of vitamin D that was microscopic. And what turned out was using 1,000 international units, which is a typical dose people would use, didn't even touch it. So I had to use 15,000 international units to get to normal, and I maintained with 5,000 international units. But it's a point where my data gave me an insight no doctor could ever have given me on how to deal with that kind of thing. And there are hundreds of those kinds of things that we'll be able to deal with in the future. And of course, the second big analytic way now is to use machine learning and knowledge graphs and transformers and AI and all of these kind of things. And I'll describe in one slide just how we're using that to approach the ability to deliver the relevant actionable possibilities to the relevant patient in the future. So the lessons we learned from the 108-person project really have been striking. So we've published now almost 30 papers from that data set. And each of those papers is a different glimpse at complexity in the individual. And I'm going to just give you a couple of general examples of the kind of complexity we've looked at. And in the Airvale program, what we did was to take the data from the individual, and from that, we generated the actionable possibilities relevant to that individual. Then we had coaches deliver the actionable possibilities in the context of what this meant for them and what it would do short term and what it would do long term. And then it was up to them to actually carry out the actionable possibilities. With the coaches, we had enormous success. And people stayed in the program almost all the way through. And I'm not going to go into, I could give you 20 minutes on why Airvale was the greatest company I ever started in terms of pioneering the future, but it was the worst I ever started in terms of absolute failure to make money. And those are not paradoxical statements whatsoever. And anyway, it was a very successful program, and we'll talk about the different data types. So we had 6 major data features. So the whole genome we did with the variants, and then the proteins and metabolites and clinical chemistries are all molecules we can measure in the blood. The gut microbiome assess the diversity of microbes that you have in your gut microbiome. And then for physiologic measurements, we use the Fitbit and so forth. And what was really important is with these things, we were one, optimizing wellness, two, having very early detection of transition from wellness to disease and with the ability to reverse it. And of course, it lets us take big data and do very powerful things at looking at major chronic diseases in ways people haven't looked at them before. And we'll talk just a little bit about that later on. So what are the lessons we learned from this? There are 7 classes of genomic variants that give us actionable possibilities. And in fact, these number way more than 10,000 actionable possibilities. And I think one of the biggest crimes in modern medicine is virtually none of these have been delivered to the physician now. There are few exceptions, but some of them. But the pharmacogenomics, those are variants that allow you not to use drugs effectively, or they can make drugs very dangerous for you. And there are at least 100 of those that we could use. The polygenic scores you've probably heard about, they let us assess genetic risk now for more than 200 wellness states and disease states. And I'll just tell you without going into evidence, one, the highest risk people for disease states are poised at a point where even slight modifications can push them from a wellness state to a disease state. So if you're really at high risk for a whole series of things, your physician should know about that and should know the kind of transitions that are warning signals. And there are beautiful warning signals for that. The other thing is, for most diseases, high and low risk people should be treated very differently. And we can talk about examples of where that's true. Rare diseases, there are probably 10,000 of them now, and about 5 to 6% of the population have one of these rare diseases. So they're very rare, but there are so many of them that in the population, your chances, 1 in 20, of actually having these and knowing about them at the beginning really can save people a lot of difficulty of diagnoses that go on and on and on and often not received. And lifestyle genetics, we have variants that deal, for example, with athletic injuries. We got at least 300 of those variants. And in many cases, if you know you're susceptible to ACL tears, there are things you can do to avoid it. So I remember I went to Pete Carroll, who was the Seahawks coach, and I gave him this pitch about, look, we could really tell you which of your people are susceptible, and then we could make recommendations about how to avoid those ACLs and everything. And Pete Carroll loved the idea. His players categorically refused. They said, you mean you're going to tell the owner what my genetic deficiencies are so they can use that as an excuse when we negotiate? So we never got any place. A second area that is really interesting is we can use the blood analytes, any one of the 3 different classes, to actually calculate the biological age that you have. That's the age your body says you are, rather than the age your birthday says you are. And the idea is the lower your biological age is relative to your chronologic age, the healthier you're aging. So what we were able to demonstrate is, one, all 3 analytes gave us biological ages, and they were different in interesting ways, and we won't go into that now. But one thing that was really striking is men and women, on average, lost a year of biological age per year they stayed in this wellness program. And this is the only really valid study I know of biological age that really correlates an increased wellness state and so forth. The second thing we could do is we could use it to determine the biological age of major organs like your heart and your kidney and your liver. And people could be very healthy in one context and very unhealthy in the other. And it was very useful kind of information. The other thing is, these are all metrics that can give you insights on how you can optimize biological age in different ways. And the epigenetic marks, which are what biological age really started on some time ago, don't do that at all. They don't give you any insights into how you can improve it. Disease always increases your biological age strikingly. We had 2 individuals with severe COVID that had more than 20 years added on above their biological age, and actually neither of them lived. So we didn't do a methodical study, but it was an example. And the other thing we're doing is the metrics for biological age. We need to look at between 20 and 50 features. So the really interesting question you can ask is, what are those metrics for biological age actually looking at? So what we're doing now is we're putting these health metrics into knowledge graphs that connect us with the dynamic biological networks and community relationships of wellness, so we can see just exactly what we're looking at. And that's really important, as you'll see in the next slide, because we can actually look at other metrics for health too. And we have a biological BMI metric, which is better than anything out there for measuring metabolic states and so forth. And it's very rapidly done, so you can really look at diet changes and all those kind of things that you could never see if you use the height and weight measurements that are classic for this. The health metric we've just finished is a frailty metric that is absolutely independent of age. So it really is measuring the things that make you frailer. So, and we can measure immune function. I'll talk about that tomorrow. And we can actually measure brain cognition, and we can measure 25 different cognitive features. And if you're deficient in any of them, there are ways to reconstitute those deficiencies. And I think that's one of the most important things we have to do if we're going to age successfully. If your body is perfect and your mind is gone, there isn't much reason to live on and so forth. So all of these things we'll put into knowledge graphs and integrate into the global scope of biological knowledge, the features that these things have. So, and the final thing I'll talk about here is phenomics is really a discovery-driven approach. And for many people who write NIH grants, that's an anathema, totally. But it is discovery-driven because humans are so infinitely complicated, you can't even begin to guess all the things very large data sets might generate. And I've talked about 4 or 5 of them here. We have probably 30 of them in comparable kind of detail and everything. But one thing we're doing with the Buck Institute, which we've partnered with basically to do this kind of thing, the Buck Institute is a focused, intense look at the 14 hallmarks of aging now and trying to understand those in detail. And what we really want to do is, using these knowledge graphs and AI, we want to fuse together their knowledge into the much larger context of scientific wellness knowledge and everything. And I'm convinced that that will give us a lot of the tools we need to really optimize the health span to 90 and beyond. So that's kind of the current state of the art and where we are for optimizing wellness. And let me just say, these 5 different health trajectories that I've talked about are enormous aids in optimizing wellness that are really beautifully nonspecific, but very powerful, as we showed with biological age. So now we're going to look at the other side, and that's prevention. And the scrapie disease that I talked about earlier was really an interesting one because you induced the scrapie by putting prions in, and that infected the brain and triggered the onset of the neurologic disease. And what it gave us the ability to do is look at the 24 months of evolution of the scrapie disease before the mice were actually terminated. And what we were able to beautifully show there is you began with 1 or 2 disease-perturbed networks, and it expanded exponentially. So by the time you got to a clinical diagnosis, there were at least 4 different major classes of networks that had become disease-perturbed. So if you have all of these really terrific precision drugs, and you used one to attack that disease, you'd have the other 3 things to deal with. And that's the essence of the problem cancer has. There is no good approach to cancer today. I mean, if you want to go through 8 successive $100,000 a year kind of drugs, you can do that kind of stuff. But people have to ask how they want to live and everything. And the airfail population was interesting because in the 5,000 people, 137 transitioned to chronic diseases. 30 of them went to cancer, and we took 10 that went to cancer and looked at the bloods prior to clinical diagnosis. And we showed one in every single case. There were small sets of proteins that were elevated. And in all cases, some of the proteins that were elevated were members of networks that were known to be disease-perturbed in the type of cancer we had. So the important point was they gave you a starting point for where you might begin therapy when it's simple with a network or 2 changed rather than when it's very, very complex. And that gives us then the ability to have a phenomic medicine where you do this early detection and you identify the simple network with appropriate kinds of drugs. And the drugs, I think, that are going to be most effective, I'll talk about tomorrow. These are peptide drugs, and I'll tell you why I think that and everything. But the idea then is you can bring people back to normal without ever letting them get the disease. And the important economics of this argument are the current healthcare costs in the U.S. are close to $5 trillion a year. 86% are chronic diseases. If we can eliminate in a 5-year period half of the chronic diseases, you could have trillions of dollars in savings. And that's the kind of argument we're going to be making to the, Trump administration for the million-person project. And of course, again, you can see how important wellness, how important transitions, and how important being able to deal with the disease is all about. The final point I'd like to make is classic wellness, which is diet and exercise and sleep and stress and community, is really important. There's no question. And as an individual, it's up to you to find out which of those things are optimal for you. And there's a lot of information out there on it. And there actually is a book by Eric Topol called Super Agers. And the reason that book is really terrifically worth reading is he focuses on all the evidence-based data that we have now, and it's an enormous amount of data. And look, I don't know that a layperson, it might be a little detailed for them, but if you have even any background in medicine, that is absolutely a terrific book. Well, I had a podcast with Eric not long ago, and it was one of the most enjoyable podcasts I've ever had because we're certainly highly in sync with one another. But anyway, a lot of the companies out there that are classic wellness, an awful lot of what they push is not evidence-based at all. And you have to be very careful about those kind of things. But the other point I'd like to make is if we expand into data-driven health, you'll see that for each of these major omics, you get all sorts of new actionable possibilities that extend you way beyond classic wellness. And for the microbiome and the metabolome and the proteome and wearable data and so forth, there's enormous kind of expansion. Of course, what that does for the individual is it lets you focus on the relevancies for the individual of certain actionable possibilities. And with that data dimensionality, then you can think about therapies and interventions and drugs and all sorts of things that allow you to get there. And so scientific wellness, the optimization of wellness, and the avoidance of disease, I think, is really going to be the future. And it's the reason I think most of the kids that are here may have a really great chance of living into the 90s fully functional. That would be terrific, and maybe some of the rest of us too. So anyway, so actionable possibilities, as you can see, are multiplex: optimizing wellness and aging. Ameliorating deficiencies of the genome is really key. And of course, one of the really exciting things about the 10,000 rare disease we're going to get is, my guess is in less than 5 years, we'll really have the ability to do genome editing effectively, and we'll be able at birth to cure people of those major kinds of genes. So that, I think, is really an exciting idea. The ability to look at the 5 different trajectories we talked about is really a key to optimizing wellness. And for older people, being able to deal with frailty is really key. And actually, for those of you who are taking GLP agonists, which we'll talk about in the next slide, you ought to be doing the frailty assay on that, because one of my friends told me this story of one of the earliest uses of this was a woman that was about 400 pounds, and she lost 150 pounds and found she couldn't get up out of the chair. And the idea is, with these GLP inhibitors, you lose fat and you lose muscle. And there are arguments about which you lose the most of and everything. But these are, one of the things about these GLP-1 inhibitors is they are actually an ideal drug for doing certain things. And there's really good evidence-based data for things that deal with diabetes, things that deal with obesity, and a variety of other kinds of things. And I think they're going to be very, very promising for people that won't have the discipline to do exercise and diet and all of those kinds of things. But they have real side effects, and they have really intolerable GI effects for some people. And I had a really good friend who lost half of his pancreas before they realized it had catalyzed necrotizing pancreatitis that had to be removed. So they aren't without danger, but they have enormous power. And with the peptides we'll talk about tomorrow, I think there'll be many more of these kinds of things that we'll be able to do it in the future. So where are we taking the future of this health? So Phenome Health, the vision is a world where everyone is empowered by their data to improve wellness and prevent disease. And we haven't told you how we're going to persuade them yet. That's for you to figure out. But the mission is really to develop the tools and the insights that drive this, and to develop the partnerships that will really catalyze it. And that's something very important that we're thinking about. So our big data efforts in the future are going to use probably 10 to 100 times more data than we did with Aravale. But we're developing new kinds of technologies as well. So the polygenic scores, I think everybody should have all of those, or your physician should have them for reasons I've already given you. One of the things that I love arguing with AI specialists on is their arrogant claim that AI is going to be able to solve all the problems of biology. And, the real fact is AI takes the tokens, takes the data you give it, and it makes the tokens that allow it to make these predictions and all. But the point is, the data that we give it is only a small fraction of the data that interrogates the real complexity of human beings. So the second thing we're talking about is using saliva and a multispectral analysis to analyze it. And one of the first things that we were able to show is in saliva, it takes this instrument 3 seconds to distinguish a COVID-infected individual from a normal individual. So we're doing clinical trials with this assay to convert transitions into spectral analyses that let us look at other aspects of complexity. And we've peeled this onion of complexity from some of the outer layers, but we've got to get more data types to get into the central part. Voice is going to be an incredible diagnostic tool. There is absolutely no question about that. We have a partner in Luxembourg, again, that has done some beautiful things in that regard. And then finally, I just emphasize brain health and the ability to deal with cognitive abilities. And the same exercises that optimize cognition can be used to really strengthen the autonomic system toward the good side of it, away from the sympathetic to the parasympathetic system, and so forth. So on AI, we've developed a database that can do all the sophisticated multi-omics in any one of the 3 types of clouds. And what we've done in that database is embedded 2 different knowledge graphs that essentially tie us to all of the known public data with regard to networks and communities and so forth. And what we're able to do then is to take these health algorithms and put them in and learn lots of new things to actually take the actionable possibilities, of which we now have probably 600 that we're running through this thing, and take the ability of putting in large population sets like Aravale. And we have agents that can analyze those data in very specialized ways that can feed into a transformer. And of course, the transformer can take the unique features of the individual and specify then, in the context of these data, the actionable possibilities that individual needs in a prioritized manner. And we can use chatbots to really help coaching with the whole thing, and I won't talk about that. 2 general opportunities exist now. One is to take cohorts of individuals like we did Aravale and return their results to them. And we're trying to do that. And that still has some challenges, and we'll talk about that a little bit. But the second thing is to use this big data approach to create very powerful clinical trials for the 4 major kinds of chronic diseases. And we've used it for the last 5 years with diabetes, and we have an enormous amount of data on diabetes. And I'll tell you a little bit more about what we're going to do with that in just a moment. So the active projects we're working on is we recently got a $52 million grant from ARPA-H for 5 major phenomic projects. And one is to look at the rhythms of the blood analytes and to see which are stable and which are unstable, and to know how we can assess them as we move into larger and larger blood analyte numbers and so forth. A second thing we're doing, which is really interesting, is we have a cohort that has followed diabetes from the point of 700 very high-risk individuals for 15 years, every 3 years having an enormous analysis from the diabetes point of view and glucose testing and all those things. They have bloods all the way across, so we can do multi-omic analyses. And of the 700, of the 400 they started with, 70 has type 2 diabetes. And we'll take 70 controls and compare them for the entire life history of diabetes. So it'll give us the subtypes present in diabetes. It'll give us the transitions to the complications of diabetes for the different subtypes, and it'll give insights and therapies one can think about. And of course, in the future, we're going to be starting a diabetic trial, and the GLP-1s will be a very central part of what we're doing there. And that's with South Carolina. We have a partner there, and we've raised $21 million over 2 years to start a 1,000 subject type 2 diabetes trial. And I think we'll learn more in that 2 years together with this other study than we have in the last 10 years about diabetes. In Alabama, we're doing 50 patients with Alzheimer's disease. And without going into a lot of detail, we've used digital twins on Alzheimer's to show unequivocally it's really basically a metabolic disease. And it being a metabolic disease and knowing exactly what the nature of the mechanism is gives you a whole new insight into new early diagnostic tools and interventional kinds of opportunities. And we'll be looking at that in the same context. And we're looking at 60 patients that are poised for heart failure with Tampa General Hospital. In the pregnancy, we're going to actually be collaborating with Stanford on a project where we take 100 to 200 women. And what we want to do this time is get a baseline before they get pregnant and then be able to follow them into pregnancy and all the way through pregnancy. But then we want to take the infants for a period of 8 to 10 years and do omics on early childhood development. And I think, again, those are all absolute data deserts at this point in time that we can populate with information and so forth. And we're starting an international million-person project focused on Asia with a colleague in Turkey, and I'd be glad to answer questions about that. We have partnerships for the future. Luxembourg, we're going to do a whole series of things with them. And we're thinking about Airveil 2.0 very actively. And I would love to get an introduction to Alice Walton and see if I couldn't persuade her what she needs. I mean, her view of the medical school she's starting now is on well-being and prevention. And this is exactly what we're talking about. And giving the students these kind of insights, I think, is really going to be key. And then we'll talk in a moment about a million-person initiative for the Trump administration. And I'll just say a word about rural health. So as some of you may know, the Trump administration made $50 billion available supposedly to all the states. We'll see where it goes. But anyway, we have really terrific connections to Montana and to Alabama, and really good partners in those states. So we're going to go in and try and do rural health in a big-time, data-driven way that looks at body, gut microbiome, and brain as well. And for example, in Montana, and I didn't know this, a third of the kids that are in the 5th or 6th grade are struck with depression, and incredibly high rates drop out and never finish school. And so there are very good ways you can deal with depression, I think, using Brain HQ and some of the cognitive abilities that we have. Anyway, we're making rural health projects and so forth. So you should think about something like that. Again, we could give you a lot of advice about at least how we would do it. Whether the blue states will really get some of this money or not, I think is a question we have to worry about. Education. So the 4 Ps we've talked about, and as I said, the first 3 are science, and I hope you can see we think we have those reasonably under control, especially with the million-person project. But the participatory, it's psychology and sociology, it's economics, quite obviously, and education. And we have a lot of information about these kinds of things. And I'll say that there is a group we're working with that's actually working on the licensing of physicians to do this kind of data-driven medicine in the future. And they've got some very good people working for themselves. And the other thing that we've done that's really exciting is we've just finished a textbook on systems biology and systems medicine, and we use that to create a year-long high school course in 4 different truncheons, full-year course and everything, to essentially bring this whole vision of data-driven health to students, and especially for them to realize the potential and the opportunities. And we have it now in 8 high schools. 6 are in Washington, and we have 1 in South Dakota and 1 back east, Detroit. And so I think this could be a really powerful way to recruit both people into science and people into optimizing health and everything. So we're very excited about that kind of thing. And, talking about your own responsibility as to thinking about what this is all about, the analogy I really like is music, because, the composer writes the piece, but it's really the conductor that puts together everything that gives the piece life, right? And in a sense, the piece is your genome, and of course, your phenome is you conducting all these different kind of components and treating them and behaving them in appropriate ways, your behavior and your environment and what we can do with that. And realizing that you can take an active role and really transform yourself, I think is really important for the future. And you have to educate yourselves about the data-driven opportunities. I think in 5 years, it'll be really easy. We'll have good companies out there that really can do this well for you. They don't exist now, so you have to understand what's good and go get it for yourself. And of course, there are a lot of people here that can give you help in that regard. So the challenges of contemporary medicine then are these 5. Quality of healthcare. We're at the bottom of the top 20 nations, even though we spend 5 times as much as the next most expensive nation per patient. The escalating population and the explosion of chronic diseases and equity, not a popular thing to talk about these days, but and then the increasing costs. And the point I would make is this Human Phenome Initiative, which is an extensive extension of the Human Genome Project, is what I think is going to bring us the ability to look at 1 million people over 10 years with this kind of analysis, returning results, and to validate the quality of improved health, to validate the enormous savings that come from avoiding chronic diseases, and a whole bunch of other things we can talk about. And of course, the really important possibility is to drive the development of technologies that democratize the production of genome and phenome data, so much of it can be done at home with wearables and so forth. And one of the ARPA-H projects is to do an impedance match between the omic analyses of diabetes and the stray signals in two wearables that may allow you to transfer omic analyses into the wearables. And we think that can be done in the future. So, what are the major paradigm changes we see coming? A healthcare of wellness and prevention, and ultimately in N-of-1 medicine. That's another thing that we're doing in the ARPA-H project, which is really exciting. And the essence of what you need to do is to be able to look at your genome and phenome and extract all the features that are unusual. And those are the signals that let us map then the actionable possibilities. 2, the democratization of healthcare. So the measurements become simple, and we can think about things like rural medicine and going into the poor regions of countries and undeveloped countries themselves. And of course, I think the enormous partnership that's coming in the future, and you really have a major obligation at Irvine to teach the young physicians that AI is an incredible partner that can give them domain expertise across the whole swath of different medicine. And it isn't going to take their job away. It's going to enable you to give patients the kind of care you were never able to give them before. Thank you.
Thank you, Dr. Hood, for that phenomenal lecture. What a look at the 7 sort of turning points and helping us look into the future of what healthcare could potentially give us in terms of actual health. So with that, we have time for a couple of questions. Oh,
that's all right.
Dean gets
so you had the problem in the NFL. The players didn't want to know what you could tell them, right? Because they were worried about the consequences.
Right.
We have mistrust of science. So how do we democratize this if people don't trust us?
Well, one thing you can do on a number of these things is persuade their doctors that it's okay for them to know this evidence about their patients, and then warn them when transitions are coming for any of these different kinds of things. But I'll tell you, I would say with a little bit of education, 95% of the Airville patients wanted to know everything. This idea that patients will go to pieces, or I think it's absolutely wrong. But patients should be given that option, and if they want to opt out of it. But I don't think we should opt the doctors out of it, because they can, with polygenic scores, and you've got someone at the 99% risk level, they're really good indications that we can follow with data-driven health when transitions are starting, and you can get in there and do something before it's diagnosed chronic disease.
The comment that you've made about these patients that develop COVID and then their biological age increased significantly, were you able to look at any genomic factors that might have been involved in their poor response to the
No, it was just 2 things. So it's just we had the bloods to look at, so we did. And we didn't do any kind of study from it. But what we did show is we looked at 40 different kinds of diseases. Every single one of these diseases, the people had biological age greater than their chronologic age. And a number of them, when they resolved, it went back to a reverse if they were healthy again. So it's a gauge of your response to the challenge of disease, and it can tell you when you've changed, started to convert back and so forth.
Can you reduce your biological age at any age?
So the Airvale people were 21 to 93. And the answer is, I think you can reduce it at any age, but we really didn't have that many. Young people think they're immortal, and they don't need this kind of thing. And that's a fallacy we should get around too, because I think the early establishment of healthy habits. So my biological age is more than 15 years younger than my chronologic age. And I really attribute a lot of that to exercise, quite frankly. I've been a kind of fanatic and mountaineer and rock climbing and all of those things. And I'm not doing those things now, but that difference has held up pretty well. So
The 16 times you went to the Rose Bowl, right?
well, that was Caltech's home field, but so there were 50 people in an auditorium that held 150,000 cheering for Caltech, so it was.
So I'd like to invite Dean Stamos back up to the podium.
Dr. Hood, if you'd join me please up at the podium. We have
Okay.
a small gift for you for our appreciation. We really so greatly appreciate you taking the time to share your impactful work with all of us, and we look forward to tomorrow's lecture as well. But please, if everybody would please join me in thanking Dr. Hood. And, we have a
Thank
small
you.
token here. It says UCI School of Medicine, Dean's Distinguished Lecturer, Leroy Hood, MD, PhD, November 12th and 13th, 2025.
Oh, thank you very much. Appreciate it. Hey, I'd like to say if the students want to stay afterwards, I'd be glad to answer their questions. Okay?
We can move a little bit this way.
Okay?
And together, facing this way.
Turn on this page.
Okay.
You have
Oh,
to-
oh, okay.
You're the star. Here we go. Ready? 1, 2, 3. One more time.
Okay.
Excellent. I want to thank a few people who helped make this event possible. And then we'll invite some people up to the front if they want to say a few words with Dr. Hood, ask him some more questions, or perhaps get a signed copy of his book. First of all, I'd like to thank Dr. Shaista Malik and Dr. John Gross, who really spearheaded this whole event and invited Dr. Hood and convinced him to come out here and visit us. Dr. Gross, unfortunately, wasn't able to make it this evening. All the people behind the scenes, including especially Raina Sosha, thank you, Raina, and Kevin Wynn. Kevin right there. Thank you. And then also Jessica Banfield, Teresa Waters, Emily Dawidoff, Christine Van Doren, Shanita Moore, Jim Swenson, Michelle Heath, and Matt Miller, and all the rest of the team. Thanks so much for your hard work. And thanks again for the great crowd this evening. And again, for the lucky attendees that were already selected and offered a chance to get a copy of the book signed. And then if anybody else wants to come up, there might be a couple extra copies. We'll hope for the best. So thank you all for being here this evening.